everyone, Mrs. Hanson back again, and you've by now concluded your reading assignment portion and are back for Fischer Projections, looking at section 15.6. This is the top of page 8 in your notes. So we're continuing investigating the three-dimensional stereochemistry of chiral centers. We are now going to take a next step in the way that we present three-dimensional molecules on a flat piece of paper and introduce something called a Fischer projection. Capital F at the last name, Fischer projection. Instead of drawing these tetrahedron chiral carbons with two bonds in the plane and one behind and one coming out, say, for example, if we have a dashed wedge system in which we have a chiral center, we put two of the four bonds in the same plane. One comes out as a dash, the other comes out as a wedge. We're now going to look at the molecule from a different vantage, a different point of view, and tip the tetrahedron so that both horizontal bonds come forward. So move your eye to investigate a different vantage point, whereas now your eye, kind of looking here, you're going to be looking so that both of those are coming right towards you. So when we look at it that way, you can see that we end up having two wedges coming out, and then going behind the page would be the other four attachments. This is the beginning of the perspective of a Fischer projection, tipping that chiral carbon with its tetrahedron shape so that both horizontal bonds come forward and both vertical bonds go behind. The chiral carbon now has two wedges and two dashes. When we look at it this way, the chiral center now becomes at the middle portion of a cross in that cross formula. Very easy to draw with a little bit of practice. And it saves us the time of deciding what's going to be a dash, what's going to be a wedge when we draw mirror images. Because quickly I can see a mirror image of this molecule has X and Y still up and down. The mirror image would just switch the X and the Z position. Here is the mirror image for the enantiomers of that cross formula. So a much quicker process if we can take that step in envisioning looking at the chiral center so that two of the four atoms are coming out of the page hugging you, tucking away the other two attachments up and down. If we consider a molecule such as 2-butanol, now I drew this with you on the molecule there on your page, 2-butanol. Do you have that labeled so you can see that this OH group, this is an oxygen, this is that functional group of the alcohol, carbon 3, carbon 4. So I've written that where the carbons are in the longest chain going up and down. So the vertical axes will be the longest carbon chain. Here. So now when I think about how it's presented to me, notice that the carbon number 2 is the chiral center. Carbon number 2 has 4 unique attachments. One of them is a hydroxyl group, one of them is a methyl group, a hydrogen, and the ethyl group. 4 unique attachments. From the perspective of carbon 2, that's our chiral center, notice that the carbon leading up is going behind the page. Notice that the carbon pointing down is going behind the page. So the longest carbon chain, 1, 2, 3, 4, is presented as dashes. Notice that the carbon has the hydroxyl group coming out of the page as well as its hydrogen, and you can see those members as wedges. When you draw the mirror image, hydrogen again stays as a wedge, as does hydroxyl. Methyl still points up and the ethyl still points down. All that we've done is switch the location of what was placed on the wedges. And to make it even easier, we turn these Fischer projections by representing them as crosses, knowing that the center represents a chiral carbon. When we look up, those are always dashes. The vertical axes are always dashes. And the horizontal axes are always wedges. They're coming out hugging you from the page. So when I think about what that means, if I were to redraw this chiral carbon, going behind the page is the methyl. Going behind the page is the ethyl. Coming out of the page toward me is a hydroxyl and the hydrogen. So the perspective of a Fischer projection, if it's on the horizontal axes, those are wedges. If it's on the vertical axes, those are dashes. And we simply represent the chiral carbon as the center of a cross. And we'll say, in our mind, we know if it's up and down, that they're going behind the page. And if it's left and right, they're coming out of the page. A chiral center represented with a Fischer projection. I had to pause there. I just had a slide out of order and I wanted to pause and get reorganized. Come back and make sure that you found what I'm looking for in terms of what to write down in your notepad. So looking at the dash wedge of 2-butanol in one stereocenter, and then you drew its mirror image right next door to that mirror. So you see that dash wedge approach for both. And then I also wanted you to just include the cross structure where it says the Fischer projection formula for both in the cross section. So all four of those structures kind of filled in the middle part of page 8. The goal there was to move from a ball and stick model to a dash wedge model to what we call the cross Fischer projection. So let's begin by kind of drawing enough, get a little bit more practice with it. And we're going to look at a glyceraldehyde molecule, and we're going to practice drawing both enantiomers. Alrighty. So first of all, notice that they give us the carbons, and notice the longest carbon chain is actually going right now in terms of the horizontal axes. When I draw the enantiomer, I want to draw the tetrahedron of one enantiomer with the horizontal bonds as wedges, the vertical lines as dashes, and then just arrange those four groups from the chirality center. Carbons will go vertical. So here's my carbon number 2. It is indeed the chiral center. Just to emphasize, we can see this is the chiral center. So when I begin placing the chiral center, that's the origin. That's going to be all four bonds attached. Now as I go in any direction, this is kind of what we're saying, there's 4 directions here. I want to emphasize that the carbon chain should go on the vertical axes. So I'm going to show the CHO, just arbitrarily choosing it up, and the CH2OH going down, the longest carbon chain. Then I can place the hydrogen and hydroxyl group left or right, it doesn't matter, because this is what you envisioned when you drew that. You knew that going behind the page were both carbon CHO group and the CH2OH group, and coming out of the page is little bow ties here, the OH and the H. We just drew one enantiomer. Now that's the dash wedge approach. The Fischer projection says make a cross. The cross has the chiral center in the middle. We then place CHO at the top, CH2OH at the bottom, the H in OH. The carbons went vertical as we began drawing our first enantiomer. Now, there were many choices of how to do that. The important part is to make sure that the longest carbon chain goes indeed in the same vertical plane. Then you're going to draw the second enantiomer by arranging the substituents in the mirror image so that they're the reflection of the first. Then you just simply make those turn into crosses. So step by step, draw the compound. Notice the horizontal bonds came forward. That's the hydrogen and the hydroxyl group coming forward. The vertical lines went straight back, and we're emphasizing to place the longest carbon chain in the vertical position. Carbon 1, 2, 3. That's the longest carbon chain. We arbitrarily selected the hydrogen to the left and the hydroxyl group to the right. When we draw its mirror image, the hydroxyl group is to the left and the hydrogens to the right. The reflection of one molecule. These are known as enantiomers. Now with the Fischer projection, we take the bond wedge, the dash wedge bonding system, and just simply turn them into crosses, where the chiral center is at the center of the cross. And then we know just visually that it's dashes going up and down and wedges coming left and right. We just drew a Fischer projection. How easy, correct? We drew both enantiomers, randomly selected what would be left and right, and just drew the mirror image. Let's try some more. I'm going to flip the page and see some more examples of drawing Fischer projections. In letter A, the chiral carbon is at the center, and I have a methyl group up, chlorine down, hydrogen, bromine. So all I have to do is draw a cross, and now I know that the methyl group and chlorine group are both up and down, representing the dashes. The hydrogen and bromine, left and right, representing the wedges. That is a Fischer projection from the dash wedge formula. We can draw its enantiomer. How easy is that? The enantiomer would have bromine to the left, hydrogen to the right. These are non-superimposable mirror images. They are called enantiomers. Chiral centers in the middle of the cross. Here's letter B. I noticed the chiral carbon in the center, so it's going to be the center of the cross. Up above is Q, down below CH2Cl. To the left and right, we complete hydrogen to the left, hydroxyl to the right. Drawing its enantiomer, we just flip the positions. Keep the top and bottom the same, but just flip the positions to create the mirror image of those that are on the horizontal axes. Here's a couple more. This letter A, we have a carbon in the center, leading up to an aldehyde functional group, CHO, leading down to a methyl, leading over to an OH, leading over to an H. You want to convert that to a cross structure. I didn't do that when I was talking. We need a cross structure to form a Fischer projection. Its enantiomer, its non-superimposable mirror image, would simply have us flip what's ever on the horizontal axes. The H and OH exchange places. And there's its enantiomer. Letter B gives us something a little more exciting to continue with. It's got two chiral centers. So when we consider letter B, the very last structure here, we have two chiral centers. So that means my cross is going to have two chiral centers. At the top, we have OCH3. At the bottom, CH2CH3. Chiral carbon number 1 has a methyl to the left, hydrogen to the right. Chiral carbon number 2 has a methyl to the left, hydroxyl to the right. Two chiral carbon centers. Its enantiomer would simply flip what's ever on the left goes to the right. We're drawing its mirror image. Keeping the vertical axes the same and flipping the horizontal axes to the mirror image. We just drew Fischer projections and all of the enantiomers. How are these Fischer projections in each pair related? Are they identical or are they enantiomers? Well, the decision really can come from assigning spin. If you remember, to be chiral, they have to have 4 unique attachments. In order to be chiral, 4 unique attachments. I noticed that the carbon in the center has 2 like attachments. The blue carbon is in the center, but it's attached to 2 like methyl groups. Therefore, these are not chiral. And see that test, in order to have an enantiomer, it has to have a carbon center. That means that these are identical molecules. Notice that it's 1, 2, 3 carbons. 1, 2, 3 carbons. At carbon number 2 is a chlorine. So that molecule is 2-chloropropane and therefore does not meet the criteria of being chiral because 2 of the 4 attachments are identical. Therefore, they're identical molecules. All right, let's look at letter B, see what's happening here. Letter B, I'm going to focus on the center of the Fischer projection and make sure we do indeed have chiral centers. It looks like it's fine for that test. I have a COOH, C-O-O-H, which is different than a methyl group. Those are indeed different. I have a hydrogen. Those are different. And finally, I have an opportunity to find a new color. How about this color? We'll have orange. All 4 are in a different group. Now, so that does meet the criteria for being enantiomers. So now all of a sudden, in order to be true enantiomers, not only do they have to be chiral, they have to spin in an opposite direction. So remember, the other test is to make sure that they're mirror images of each other. Because you can have a chiral carbon and still have an identical molecule if they're spinning their priorities in the same direction. So let's just call the first priority hydroxyl. I'm going to number it number 1. I'll go to COOH and call that priority number 2. Just make sure you're numbering the same number to each functional group. And I'll put a number 3 on the methyl. I only need 3 attachments to spin. This is spinning in a counterclockwise fashion, whereas I spin in this direction, and that is a clockwise. Because they're spinning in opposite directions, we now know that they are indeed enantiomers, non-superimposable mirror images. There we go. Let's test one more. Again, we notice that the chiral center is at the center of the cross. So those are the 2 carbons that we're going to consider. I have a group CH2OH. I have a group that's hydrogen. I have a group that is COOH, COOH, and a group that is NH2. So yes, indeed, there are 4 unique groups, meaning that that is a chiral carbon in the center of that Fischer projection. Now, are they spinning in opposite directions? Do they have their priorities, their attachments as mirror images? Clearly, I can see that they are. This is what's a beauty about Fischer projections. If this is the mirror, the nitrogen, which is closest to the mirror, is closest to the mirror here. Notice that the top and bottom remain constant. All we did was flip the horizontals, the hydrogen and amine. But you can prove it to yourself based on spin. Let's call nitrogen priority 1. I'll call it 1. I'll make the COOH priority 2. And down here, I'll call the CH2OH number 3. Spinning in this gives me a counterclockwise. Spinning here, the same. Priority 1. Priority 1. Here's priority 2, priority 3. That is indeed the opposite. I got it. That is No, so Linda, this is clockwise, spinning in that direction. This is counterclockwise. Thank you with your patience as I worked through that error. But they are indeed spinning in opposite rotations, so therefore we know that they are mirror images, non-superimposable mirror images known as enantiomers. Perfect work. I would say it's a good time to pause the video and try these out. How are they related? Are they identical or are they enantiomers? And we're just really kind of honing in on our practice. This is an opportunity to kind of flip the page to the top of page 10 and work these 3 problems, pausing the video, and then come back when you'd like to check your work. All right, here we go. Let's check these out. First thing I want to do is find the center and see if it is indeed a chiral carbon. Do you notice that 2 of the 4 attachments to the carbon in the center are identical? They're leading out to hydrogens. Therefore, this is not chiral. There is no chiral center, meaning that these are identical molecules. Let's try letter B. With letter B, I want to bring my eyes to the center carbon and make sure that we have a chiral carbon. Oh, look at this again. Chlorines. That chiral center has 2 like attachments, just like the letter A. That means they are not chiral, meaning that they are not enantiomers. Therefore, they must be identical molecules. Let's see what letter C brings us. Bring your eyes to the center and determine if it is indeed a chiral center. We have hydrogens that are different from hydroxyls, that are different from CH2OH, and finally we have a new group here of a methyl. So those are indeed 4 unique attachments. So this is a chiral center. Now, if they are spinning in opposite directions, they're mirror images. Imagine this mirror. Is it reflecting upon itself? The OH is closest to the mirror, both sides. Notice that all we have to do to write its enantiomer is flip what's on the horizontal axes. That's all you need to do to check. Flip the location of groups on horizontal axes to create the enantiomer. Leave those verticals alone and only flip the direction on the horizontal axes. That creates an enantiomer, a non-superimposable mirror image. You can prove it to yourself. Let's call hydroxyl priority 1. We'll make the green CH2OH priority 2, and then priority 3, the methyl. Spin. This is going clockwise. Spin in this direction. These are going counterclockwise. They are indeed non-superimposable mirror images. The attachments are in a different spatial order. Enantiomers. A physical property of enantiomers is the way that they rotate light. 2 enantiomers are identical in every way: boiling points, melting points, solubility. The only difference is the way that they've attached those 4 unique arrangements around the chiral carbon and therefore interact with light differently. The way that they interact with polarized light creates a rotation of clockwise or counterclockwise spin. So 2 enantiomers have identical physical properties. They'll include things such as these qualifying remarks of melting points, boiling points, densities, solubilities, gaseous state at room temperature. 2 enantiomers differ in how they interact with plane polarized light. Remember what the term polarized means? Let's say we have a light source, and the light source is giving off wavelengths of all direction. as any light source would, the sun, a light bulb. Notice that the wavelengths coming out from the white light of this source have rotation in all directions. Through a polarizer, which is often something like a diffraction grating, if you did this in physics class at some point, physical science class, you might have used a diffraction grating, which just means that it has slits all in a parallel form. And when the light passes through this polarized lens, the only light that passes through are the wavelengths that had the same direction as the opening of the polarized lens. So now instead of going in all directions, we call this a polarized light source. Plane polarized light means that it's oscillating in a single plane. So we turn on a light bulb, which has wavelengths in all directions. We then have this light source go through a polarized lens, which changes the all direction plane oscillating into just a single direction. So these physical properties are now going to interact with this light very differently. They have identical physical properties, but they're interacting with light very differently. An achiral compound does not interact with light, but a chiral compound does interact with light in a unique rotation specific to if its attachments are spinning clockwise or counterclockwise. We say that chiral compounds are optically active. Here we had an opportunity to introduce a chiral carbon in a sample tube of this polarized light. Remember the previous slide. We had a light source coming out in all directions, going through this polarized lens, so that the only light making it through is now straight up and down, a matching wavelength, plane polarized light. If this light source, which is now only up and down, straight up and down on the vertical axes, comes into, it's still flashing this direction. This is just a light source. If you place a chiral compound in a tube that the light has to interact with, it's going to twist the polarized lens, the polarized light source, and twist it a certain degree, so that you over here are now seeing the result of the optically active chiral compound. So the direction of the plane polarized light has changed when the light source interacts with the chiral compound. Now remember, if I had in this tube an achiral sample, nothing happens. It goes straight through and comes out just straight up and down. However, with a chiral compound, the light that comes in, which is straight up and down, interacts with the chiral molecule, and you begin to see the rotation of the light spin. And it will either spin clockwise or counterclockwise, depending upon what enantiomer you've placed in the sample tube. So chiral compounds are optically active. If the rotation of the light is clockwise, the compound is dextrorotatory. Dextrorotatory. And it's told to be the positive enantiomer. Dextrorotatory is the clockwise spin of an optically active chiral compound. If you observe that the spin, the rotation of the spin, is counterclockwise, you have the opposite enantiomer in your tube. It's said to be levorotatory. Levorotatory. And it's said to be the negative enantiomer. Two enantiomers rotate the plane polarized light, to an equal extent, but in opposite directions. So if I have a dextrorotatory positive enantiomer and it rotated the light 30 degrees clockwise, I'll just say that would be the positive dextrorotatory, just as an example, rotating it clockwise 30 degrees. Well, its enantiomer, which would be levorotatory, would have the negative enantiomer designation. It's going to rotate light in equal direction, 30 degrees, but now going in the counterclockwise direction. equal but opposite. Chiral compounds are optically active and they rotate light. Label each compound as optically active or optically inactive. Do you know what? We really have been practicing this. I don't think that this is a new question at all. If I want you to tell me if something is optically active, what am I really asking? I want to know if it's chiral. Do you find a chiral center? And if it's optically inactive, what we're really asking us is to notice that it's achiral. So this question is the same question we've been answering all chapter long. We're just asked a different way. For example, in letter A, we have octane, an 8-carbon unit. 1, 2, 3, 4, 5, 6, 7, 8. I don't see any chiral centers. It's 8 carbons. They're all, like here's CH3. That can't be chiral. 3 hydrogens. All of these CH2s have like hydrogens. This is an achiral molecule. Therefore, it is optically inactive. Let's turn our attention to letter B. Here I notice letter B in the center gives me a chiral carbon. I have a Cu, a methyl, a hydroxyl, and a hydrogen. Those are 4 unique groups. Therefore, this is a chiral center, and therefore it is indeed optically active. It will rotate light either positive or negative, clockwise or counterclockwise direction. I wrote optically twice, didn't I? Optically active. There, I got it better. What about letter C? Is it optically active or inactive? Well, with this direction, we look at the center and decide, does it meet the criteria of being chiral? I noticed 2 like groups. So therefore, it's not chiral, and therefore inactive. And letter D was cyclohexane. Mine got cut off. You have cyclohexane kind of stretched out. This is an achiral compound. I see no chiral centers, so it is also optically inactive. Easy enough. So if you're asked about chirality, you're really just being asked, is it chiral? It will spin light. If it's achiral, it will not rotate light. Pure cholesterol has a specific rotation of -32. I should have a degree there because it's an angle that it's spinning. -32. This makes me go back, and I will have to say, you should memorize this vocabulary to do well on this portion. Memorize the vocabulary of the following 2 terms. Dextrorotatory is the positive enantiomer. Levorotatory is the negative enantiomer. So when I see the bond angle of -32, I have to be able to associate that with the vocabulary word of levorotatory. Just knowing that it's a negative enantiomer lets me label that as levorotatory. If the specific rotation of the levorotatory compound is -32, what would be the enantiomer? Well, the dextrorotatory, which would have a positive designation, is just exactly equal but in the opposite way. So it would be a positive 32. Think of that as going clockwise 32 degrees, and this would leave it counterclockwise 32 degrees. One is called the negative counterclockwise spin. This is called the positive clockwise spin. Equal but opposite directions. But I do need us to remember that dextro means positive, levo means negative. Compounds can actually have more than one chiral center. As a matter of fact, many compounds have many chiral centers. And that's the beauty of these Fischer projections, is being able to draw these quickly and especially be able to look at mirror images very quickly. A compound with one chiral center has two stereoisomers. They are a pair of enantiomers. A chiral compound that has two chiral centers has 4 possible stereoisomers. And you can see it take off exponentially from there. The amino acid threonine has 2 chiral centers labeled in red. Let's draw that compound into our notes. I'll call this the first chiral carbon is in red right here. How about if I highlight that one, and we'll focus our attention on the first chiral center. The first chiral center has 4 unique attachments. We have a COOH, an NH2, a hydrogen, and then a carbon that's unique from the top carbon. 4 unique attachments. It has a second chiral carbon, also highlighted in red, with 4 unique attachments. So we have what are called enantiomers, which are mirror images. So when we drew the Fischer projection of the amino acid named threonine, kind of modeling what you see on the page, we labeled the 2 chiral centers. Since there's 2 chiral centers, we can see that we have 4 different spatial arrangements. Let's take a kind of a walk-by-walk step through what I'm saying here. I'm going to redraw this just as it appears on your page. We have a COOH leading to a carbon, leading down to a methyl. And remember here, what we have are dashes and wedges. So I have an OH and an H. Here's the NH2 and the hydrogen. So really all I did was remember that a Fischer projection says on the vertical axes, on the horizontal axes, those are always wedges. And on the vertical axes, those are always dashes. And notice the carbons are in the same plane. Alrighty. So what is its mirror image? Imagine this. All we have to do is take what the original structure gave us and flip what's on the horizontal axes. We can even be simpler. We could just, instead of dashes and wedges, why don't we just keep it with the Fischer cross, the Fischer projection. So I have 2 chiral centers. I can just show that like this. The original structure had CO2H at the top and methyl at the bottom. The mirror image would place hydrogen and hydroxide closest to there, and of course the nitrogen and hydrogen on the opposite. So to create the mirror image, just flip what's on the horizontal axes. When we drew the mirror image of A, the original structure, we got compound B. Those are mirror images, the enantiomers, non-superimposable mirror images. Now, switch one of the 2 chiral centers. Let me highlight what the difference is. We're going to switch one. Notice the nitrogen is on the left and the hydroxyl group is on the right in compound A. I'm going to switch just 1 chiral center. And now coming up with compound C. Switch one of the 2 chiral centers. Don't don't switch both or you'll have structure B, but just switch one of the 2. Doesn't matter which, just switch one of the 2. And then draw its mirror image. We've now come up with a new set of enantiomers. So, A and B are enantiomers. C and D are enantiomers. They are mirror images. A turned into C by switching one chiral center only. A turns into C by switching just one chiral center. So a different arrangement. A and D are now arranged in terms of, organizing the chiral centers originally with one on each side, and now one here, those priorities were on the same side. We have a new vocabulary word to describe the compound. So now all of a sudden, A and C are not mirror images. B and D are not mirror images. That vocabulary word says they are diastereomers. Diastereomers. Those are stereoisomers that are non-mirror images. They're not mirror images because notice that letter A, the amine and hydroxyl group are on opposite sides of the carbon chain. But in carbon C, the structure C, they're on the same side of the carbon chain. Therefore, they're not going to reflect the same at all. C and D were drawn as mirror images. A and B were drawn as mirror images. They are enantiomers of one another. But A with C or A with D, any of the other two are diastereomers, not mirror images. Let's emphasize our vocabulary. The term isomers at the top is defined as different compounds with the same molecular formula. Isomers come under two different categories. They can be constitutional isomers or they can be stereoisomers. Constitutional isomers, we know, have the atoms bonded in a different order. Stereoisomers have the atoms bonded in the same order, but in a different three-dimensional arrangement. Stereoisomers now can be categorized as enantiomers, if they're mirror images, or diastereomers, if they are not mirror images. Those working vocabulary words are critical for success as you round out your practice with chiral carbons. Let's do that. Let's practice. We have 4 stereoisomers shown for us for a compound called 2,3 pentane diol. Di meaning 2. The OL shows us the alcohol functional group. We have 2 chiral carbons being presented in each of these structures. 2 chiral carbons all the way through. Notice what else? There is a methyl group all the way across. There is an ethyl group all the way across. These Fischer projections, if I drew them as crosses and made them Fischer projections, the only difference now is the way that they're attaching these horizontal attachments in this Fischer projection. Let's compare, for example, letter E has hydroxyl on both sides. What other compound has hydroxyls on both sides? Oh, you got it. See that? Those hydroxyls are on the both sides. They just happen to be on the opposite side of each other. That means compound E and G are mirror images. That word is called an enantiomer. E with G are enantiomers. Let's investigate further. Let's find, let's use orange. On this compound, we have hydrogen. Yep, here it is, hydroxyl. Top one is to the right, bottom one's to the left. Here we have hydroxyl, top one to the left, bottom one to the right. Those are mirror images, aren't they? These are also mirror images. They are non-superimposable mirror images from the 2 chiral carbons. Therefore, they are enantiomers. A with G, and F with H are enantiomers. Now that means once we have the mirror images selected, any other possible combination would not be mirror images of one another. So for example, if I did A with F, that's E with F, they're not mirror images at all. These would be called diastereomers. They're not mirror images because they're placing their hydroxyls on opposite sides. So here I have same side, here I have opposite side. That's not a reflection in the mirror, is it? Diastereomers. For letter E, I have another I keep calling that A, but E with H, those are not mirror images either. So I have that first structure E, and I looked at it with F. Nope, those are diastereomers. And we could say the same E with the H, diastereomers. Diastereomers are those that are not mirror images. What about letter G? Any not mirror images? G with F and G with H are not mirror. G. Yeah, they're not the same. G with H or G with F are not mirror images. Those are known as diastereomers. So my first track was to figure out who really are the mirror images. E and G go together, and F and H go together. Those are mirror images. Any other combinations of those letters would create diastereomers, not mirror images. Okay, how about a bit more practice? Here we have 4 stereoisomers of a chiral center 3-bromo 2-chloropentane. So again, these are Fischer projections. If I draw them as crosses, I can see that I have 2 chiral carbons. Those are what we're comparing. Now let's see, how do they arrange? And I noticed that up and down are the same, so I'm really just considering the horizontal axes. Chlorine, and here I have a bromine. Okay, they look to be the right-hand side. Here again, I have a chlorine and a bromine on the opposite sides. Well, they're not mirror images, are they? They're not mirror images, so they must be diastereomers. Alrighty, here I have a bromine and chlorine. That looks a lot like the mirror image of X, the second molecule. Let's compare here. Here's chlorine and bromine. So which 2 structures would give mirror images to one another? I notice W and Z, structure 1 and structure 4, if that's easier. And this would be structure 3, however you want to label them. W and Z are mirror images. And the interior, those 2 are mirror images. W and Z are enantiomers. X and Y are enantiomers. Any other combination is going to give you diastereomers. So which compound is the enantiomer of W? Well, that's Z. Which compound is the enantiomer of X? Well, that was Y. Which 2 compounds are diastereomers of Y? Well, anything but X. So W and Z are not mirror images of compound Y. Which 2 compounds are diastereomers of Z? Well, anything but W. So that would leave X and Y. The 2 non-mirror images are called diastereomers. Oh, you're doing great work. Turn on the video, or I should say pause the video and try these last few out. How are these molecules related? Are they identical? Constitutional isomers? Enantiomers? Diastereomers? Or they're not isomers of each other at all? Kind of the ultimate check. Give yourself some time to work through these examples and come back to me when ready, and we'll talk through them together. Well, let's go to work. Let's see. All right, so let's just talk through some out loud logic. I notice that I have really, in letter A, what I see is an ether. And I just noticed that I have an oxygen as part of the backbone. I don't see a chiral carbon anywhere. I have an ether on both sides, right? So here is the oxygen on one side. I have an ethyl group on the other side is an ethyl. We would know to call this really diethyl ether. Here I have a methyl and a propyl. So this would be methyl propyl ether. They do have the same number of carbons. I noticed that they have same number of carbons. There's 4. They're just arranged in a different order. So they have the same molecular formula, different connectivity, no chiral. There's nothing chiral about it. So I have to have enantiomers to even consider chiral carbons for that choice, and diastereomers still need a chiral carbon. And since they have the same molecular formula connected in a different way, I hope you wrote down constitutional isomers. They have different names: diethyl ether, methylpropyl ether. Same number of carbon, same number of hydrogen, same number of oxygen, just attached in a different order, giving it a unique name. Very definition of constitutional isomers. All right, let's check out letter B. All right, letter B says, I'm going to just try naming it. It's always what I start with to decide, do I have anything? I got a 1, a 2, and a 3, and a 4, and a 5. We have a 6-membered ring, making sure I give priority to the double bond. So, all right, off of carbon 2 is a methyl. Off of carbon 3 is a hydroxyl. Carbon bond between 1 and 2 is double. Do you even, let's see, how about investigating this carbon? Is that a chiral carbon? Maybe so. All right. So I have, everything is attached in the same order. So I can eliminate constitutional isomers. I'm not sure if they're identical or if they're enantiomers. Are they mirror images? And that is determined now by deciding, do we have a chiral carbon? Because if it's not, then it's just an identical molecule. But if there is something chiral, I would then investigate if it's a mirror image. So carbon 3, the way we have them numbered, does it have 4 unique attachments? Well, I can see that one of the attachments is a hydroxyl group. I'll make that a different color. So that's unique, 1. I can see that it's got a carbon, and kind of thinking about carbon in a double bond leading to methyl. Yeah, that's different here than this carbon. I should highlight those differently. And then, of course, what we don't see but we know is there is hydrogen. That is 4 unique bonds. So this you need to recognize as a chiral carbon. So it does meet the criteria of having a chiral center. All right. So in order to determine if they're the same or if they're enantiomers, we make the decision, are they mirror images? Is this a reflection? And it certainly looks that way to me. Notice that we can do the test of spinning. If we call hydroxyl just priority number 1, I'll call it methyl priority number 2. And then leading down to the carbon chains, I'll call that priority 3. Let me make those purple. 1, 2, 3. That's the direction it's spinning clockwise. How about this direction? 1, 2, 3. Those priorities are now spinning counterclockwise. They are indeed mirror images with a chiral center, and that's our very definition of an enantiomer. Not spelled right. Enantiomer. Once we found a chiral center, and just make it as easy as noticing the chiral center highlighted now in yellow. It has 4 unique attachments. Imagine a mirror right here. It is a perfect reflection. One molecule is the reflection of the other. That's what an enantiomer is. Perfect. Let's try the next one, letter C. Do you see a chiral carbon? Me either. Because do you notice that? The carbon that they're trying to catch our eye with has 2 like attachments. That's not a chiral center. So therefore, since there's no chiral center, there's no such thing as enantiomers or diastereomers. So now we have to decide if it's the same compound. Or are they not even isomers? That decision comes through naming it. 1, 2, 3, 4, 5. This would be called 2,2 dibromo pentane. How about this guy? 1, 2, 3, 4, 5. Oh, that looks the same, doesn't it? 2,2 dibromo pentane. So they have the same name, same conductivity. These are identical molecules. And one more to check out together. The last structure gives us a Fischer projection. I see that there's 1, 2, 3, 4, 5 carbons in the longest chain. Carbon 2 and carbon 3 are chiral centers. That's the same here. 1, 2, 3, 4, 5. 5 carbons in the longest chain. So we know because they have chiral centers that they could be enantiomers or diastereomers. Those are now our 2 choices. Let me write that. Since there are 2 chiral centers, that leaves us the following choice. Are they enantiomers, meaning they are mirror images, or are they diastereomers, meaning they are not mirror images? And that just has to do with envisioning the reflection. Over here, the chlorines are on opposite sides of the chiral carbon. And here, they're on the same side of the chiral carbons. That's not what a mirror would look like for superimposing an object. Therefore, they are diastereomers. They contain 2 chiral centers, but they are not mirror images. Therefore, we'll label those as diastereomers. You've done great work on our chapter today. You have a little more reading to do to complete your note pack. I'd like you to read about the human bodies, the sense of smell, and how that relates to the special shapes of molecules. Pick out your 3 to 4 most important points and detail those to wrap up your note pack for Chapter 15. I'll look forward to reading them real soon.